We're going to do a little section called Graphs of Rational Functions in the Khan Academy, and we've got ourselves a function here. That function right there. So if you would, go ahead and write that guy down in your journal. It says f of x equals q of x over x squared minus 5x minus 24. They're like, what's q of x? I don't know, some function. All right, so we're not going to focus on q of x. What are we going to focus on? The denominator. Now, there are two things that can happen in a rational function in the denominator, but we got to get the sucker factored. So what's the factor of this baby? X minus 8, x plus 3, because negative 8 plus 3 is negative 5, and negative 8 times 3 is negative 24. So right now, what are our numbers that we have to be wary of? W-A-R-Y, wary, concerned about. 8 and negative 3. Now, in a rational function, these babies could be a couple of different things. One of them, they could create some of these horrible things that you don't want to run into, called vertical asymptotes. Trust me, live long enough, got to watch out for them asymptotes. All right. You could have a vertical asymptote at x equals 8 or x equals negative 3. But what else could they be in the denominator? You could also have this thing called removable discontinuity, which are referring to, sometimes back in the day, we just called them holes, little tiny holes in the graph, all right, where you can plug in a number, but it won't work. It'll make it undefined. Now, what happens when you have that? If we had a hole, then what could q of x have as a factor if we had a hole? It could equal what? An x plus 3, where they would what? Cancel out, and that's what would create a hole. Or if you also had an x minus 8, q of x could also equal x minus 8. Then these babies would cancel out, so you could have removable discontinuity. So what am I searching for? I'm searching for any asymptote or any hole at what two numbers? X equals 8 or x equals negative 3. So I'm going to investigate, and I'm going to choose the person to put into jail. All right. I said x equals 8, right? Is that an 8? No. Not going to choose A. You're free. Ooh, is that an 8? Yes. Ooh, is that a negative 3? Ah, B's looking pretty cuffable. 6 and a negative 4? Not even close. 2 and a negative 1? If it's not B, then slap me silly and call me Sally. Good thing I was right. All right. Ooh. Now we have something not in the denominator. We have something in the numerator. So put f of x equals, if you're watching this and wondering, is this video done towards the end of the school year when all the teachers are about to go mad? The answer is yes. It's towards the end of the school year. We're all about to go crazy. You ever heard of the phrase going postal? Well, some of our teachers are about to go, well, we can't go postal. I don't know where we go. All right, so here we go. Can I factor this guy? Heck yeah, I can. What are the factors? X plus 7, x minus 3. I agree, because 7 minus 3 is 4, and 7 times negative 3 is negative 21. Now, in the numerator, we don't have to worry about any asymptotes in the numerator. But we do have to know about two things that could happen in the numerator. You could have a 0, or you could still have this concept called removable discontinuity. So you could have a hole or a 0. Where could they be located? Either at x equals negative 7 or x equals 3. So I'm searching for any 0 or removable discontinuity happening at one or both of those points. Okay? Like, I don't understand. What are you talking about 0? So listen, I'm going to give you a quick little example here. Ready? What if I had x plus 7 and x minus 3 over x minus 3? Let's say that was the function. Then I'd have a removable discontinuity at x equals 3, and I would have a 0 at x equals negative 7. But if I would have had, say, x plus 7 times x minus 3 over x plus 7, then these would cancel out, and I could have a 0 at x equals 3 and a removable discontinuity. I'm just doing RD for short because it takes a lot less time, at an x equals negative 7. So I'm just searching for a 0 or removable discontinuity at one of those two numbers. Why? Because it's in the numerator, and I don't have to worry about what in the numerator? Asymptotes, because they're only in the bottom of the fraction. Yeah. Sorry, bad joke. All right, so negative 7 and 3. Negative 7 and 3. Ooh. So I have a 0. Hey, right here, is there a 0 right there at a 3? Yes. Okay. Ooh. Was it 3 and negative 7? Ooh, look right there. If you, I can't really zoom in from here, but there is a 0 right there at a 3, and there's a 0 right there at a negative 7. Here, there was a removable discontinuity at a 3, but at a 7, there's not a 0. Okay, so let me go back to my work. 3 or a negative 7. So I'm going to say 0 there, 0 there. I'm going to choose B. Okay, so I had to search for that. There was a removable discontinuity at a 3, but what else could there have to be? Either a removable discontinuity or a 0 at the negative 7. Okay, ooh, here we go. I like this. What in the world? All right, here we go. Ready? We have this big long thing right here. Okay? All right. Now, interestingly enough, if you put 0 into all areas of this function, you plug in a 0 for all of the x's into everything. What's the only thing you have left standing in the numerator? A 5. And what do you have in the denominator? Which means you have a y-intercept at a negative 5. If you plug in 0 anywhere into a function, it gives you the y-intercept every single time. So what am I looking for? I'm looking for a function that has a y-intercept at negative 5. Now, what did I do again? I plugged in a 0 there. 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 Where's my y-intercept for A? 7. Where's my y-intercept for B? 3. Where's my y-intercept for C? Ooh, I think I found him. And where's my y-intercept for D? That's not it. So I'm going to choose C. Wow, it's like I'm getting all these right. Wonder if I know what I'm talking about. Possibly. Ooh, let's do another one. We'll do it quicker though. Ready? X minus 7, x plus 2 in my numerator. What number can make that equal to 0? 7. What number can make that equal to 0? Negative 2. But this could be a 0 or a what? It could be a 0 or it could be removable discontinuity at a 7 and a negative 2. 7 and a negative 2. I don't see anything here. Nothing. Don't see. It's not it. Okay? So 7. Ooh, 7. All right. No, I don't see negative 2. No. Let's look. Oh, look, I found it. Look, there's a 7. There's a 0 right there. And then is there a 0 right there at -2? Because they're counting up by 2. So I found a 0 in there and there. So that's what I was looking for. I was looking for the zeros. I was also looking for removable discontinuity, but I didn't see any removable discontinuity, so I'm choosing B. Okay. Oh, look at there. Here we go. If I factor the bottom, it becomes 2x squared minus 16, which becomes 2 parentheses x plus 4 and x minus 4. Ooh, what could be, not knowing what g of x is, what could be bad numbers to plug into the denominator? -4 and +4. So I could have a vertical asymptote or a removable discontinuity. So I could have a vertical asymptote or a removable discontinuity at x equals -4, x equals positive. Oh, I guess I should just stop talking because, like, is that an asymptote? Is that an asymptote? It's like right in front of me, and it's in orange, and I didn't even know. It's the same color of everything. I did not do that on purpose. I was just doing the problem that happens to be the right answer because look at there. You got your vertical asymptotes right there. It'd be funny if it was wrong, but it's not. All right, last one. The reason I kept going is I finally had to get to the final one. Finally. Does everybody see how that says 14x to the power of 4, and that says 7x to the power of 4, and we don't know anything else about it because we just don't care because we're focused on the highest powers? We know what our horizontal asymptote is because it's got to be what? 14 over 7. Now you're like, what the heck are you talking about? If, and only if, that power is the same as that power, then all you have to do is take this number and divide it by this number, and you're done. So you just take 14 and you divide it by 7. Now, y is the only reason I'm allowed to do that because these powers are the same, and that gives me my horizontal asymptote, which is at a 2. So I'm just looking for a horizontal asymptote that is at a 2, and that's it. I'm not going to tell you which one it is, but it looks like it's this one. Okay? There's my asymptote. Not vertical, but what? Horizontal. Oh my gosh, yeah. Look at all these other ones. That one looks like it's at 0. That one looks like it's way, way, way up here. And this one looks like it's right here, kind of like at a -1. So I'm going to say 2. And that's all you have to do. Okay? Okay, we'll just do one more. What's 10 divided by -2? -5. So we just got to find a y-intercept at -5, y-intercept at -5, oh, there it is. Y-intercept at -5, just to get another 100. And that's it. Have a good day.